In this video, we're going to do some examples of writing equilibrium expressions for different reactions, following the rules we learned about in the previous video. I'm going to do one with you, and then I recommend that you pause the videos and then try the rest on your own, and then play the videos to check your work. And it's really important to get that exercise of, pausing, practicing, and then assessing yourself. So here's our first system over here. We're going to write an equilibrium expression for it. We don't have numbers. We're just writing an expression for it. So what I would first do is put the KEQ is equal to, it's a big K, not a small k, because that's different from the rate constant. I would make sure my equation is balanced. It looks like it is. Iron 1, and one of these, and one of these. Okay. So this is my product. So my product goes on top. So Fe, the concentration of FeSCN, 2 plus aqueous divided by, now we make sure there's no coefficient, or there is, it's a 1, so it's to the power of 1. I don't really have to write that down. The concentration of the reactants multiplied by each other. So SCN minus aqueous, again to the power of 1 here, times Fe 3 plus aqueous to the power of 1 again. So I was able to include all these terms in the equilibrium expression because they were all aqueous. But remember, if they were solid or liquid, I would not have included those terms in that expression. You can try the next one and then check your work. So pause it, check your work. So here I'm doing KEQ, big K, EQ, is equal to, so the product is NH3. And there's a 2 there, so that's going to be squared over N2 gas. Don't put for your states. I should do that here too. Gas. This is a coefficient of 1, so just to the power of 1, times concentration of H2 gas to the power of 3. I was able to put all those in because they were all gases. All right, now we're going to try our third one here. So look very carefully. Everything looks balanced to me, but you'll notice that we only have 2 aqueous things. There's no gases. We have liquid and solid. And liquid and solids don't change in their concentration, so we don't include them in the equilibrium expression. So we're going to do KEQ is equal to, so we have that K plus AQ to the power of 1, because there's a coefficient of 1, over the H plus AQ to the power of 1, because there's a coefficient of 1, and we don't include the KOH and the water in the equilibrium expression. And so that is how you would write equilibrium expressions for different systems at equilibrium. You'll notice we have the double arrow there, okay, to indicate that these systems are going towards equilibrium, okay. Now, there'll be another video that you can click on to watch how we derive the equilibrium constant from the little k, from the rate constant. You can click on that to watch that. Before we jump to that, though, I recommend we go to the magnitude of equilibrium first. So there will be a point where you're going to be calculating the k value. You'll be making a k equilibrium expression, and you'll plug in some numbers given to you. And for certain values of k, that'll tell you something about the equilibrium. So if you have a k value that's greater than 1, we usually say much greater than 1, that means that the equilibrium is going to favor the products at equilibrium. What that basically means is that, so if you have A plus B produces C, by the time equilibrium is reached, you'll basically have more product than reactant at equilibrium, okay? Because it's more towards the right side. If you think about it, it makes sense because your equilibrium expression is product over reactant. Now, if your K is less than 1, much less than 1, it means that the equilibrium will favor the reactants at equilibrium. So it basically means that at equilibrium, you'll have more towards the reactant side, concentration-wise, compared to product. But if your K is equal to 1, roughly equal to 1, it means that the concentration of the reactants, and products, they're basically very similar. They're nearly equal to each other. So K larger than 1, your products are favored. You have higher concentration of products compared to reactants. K less than 1, you have higher concentration of reactants compared to products. And K about equal to 1, you have equal concentration of reactants and products at equilibrium. Okay? But remember, equilibrium does not mean that you have to have equal concentration of both. It simply means that your concentrations have stopped changing, and you could have one of these three scenarios, and you can tell which scenario you have based on where your K value lies once you actually calculate it. So as you can probably guess, our next step in this series of learning videos is to essentially practice calculating the equilibrium value from an equilibrium expression and some concentration data, and then making a conclusion as to whether we are favoring products, reactants, or neither. In other words, we're equal. So in this video, what did we see? We focused on making equilibrium expressions using our equilibrium expression rules, basically not including liquids and solids in those expressions, and doing products over reactants with the exponents as the coefficients that we saw in our equations. And then we briefly saw what different values of K indicate regarding the equilibrium condition, meaning are there more products at equilibrium or more reactants, or neither? Are they equal? Later on, I recommend that you go and watch how to derive the equilibrium constant from the rate constant little k. But in the next video, we're going to go and watch and learn how to calculate equilibrium concentrations.